Uh, Good afternoon, ladies and gentlemen. This is Professor David J. De Los Reyes. My topic this afternoon will be the estimation of the world population using differential equation. World population using differential equation. It is on the topic variable separable. Okay, let's proceed, guys. I will try to read the problem regarding the estimation of the world population. Okay, this is DE11, Differential Equation Lesson number 11 on my channel, Professor David J. De Los Reyes on YouTube channel. It is on the topic course differential equation. Subtopic variable separable. The topic for this afternoon will be the estimation of the world population using differential equation. Okay, since the problem is a little bit long, I will not write it on the board. So to minimize the writing, I will just read from my notes. Okay. Somebody's calling me. Okay, guys, so I will try to read the problem. I just waited for the call to stop. Okay. My audio is being removed, you know. It is estimated that the Earth can support a maximum population of 5 billions. It is further supposed that the rate of increase of population is jointly proportional to the population and to the difference between the population and the estimated maximum. That is, the given condition is dP over dt is directly proportional to the population and the difference of 5 minus p. That is the condition of the problem. Okay. If the population was 1 billion in 1900 and 2 billions last 1950, by the year 1950, they say the Earth population was 2 billions. The question is, what will be the population in the year 2000? We are now past year 2000. It is now 2022. Okay, let's try to compute our Earth population by the year 2000. Because I googled the population for year 2022. According to my Google, the population this 2022 is actually 7.7 billion. And the problem is asking, what is the population by the year 2000? We are already past year 2000. The Earth population by year 2022, I use Google, okay, 7.7 billion. So supposed to be, what we will get will be less than 7.7 billion. Okay guys, let's proceed. The problem says that the rate of increase of population with respect to time is directly proportional to the population and the difference between the maximum population 5 billion minus p. Scientists predict that the maximum population is only 5 billion. I think there is a little problem over here because I googled the population for year 2022, it's already 7.7 billion. So this got a little, error. Oh, that's just what you call this. I think they try to bring out a relation between population and time, and they say that the maximum population, they predict that the maximum population is 5 billion. Okay, but this is to be got a problem already because year 2022, our population, the Earth population is 7.7 billion. Okay? Oh, this is just for illustration. Okay? But it got a relevance on the computation of the world population at any given moment in time. Okay, I will erase this one. The problem says that the rate of increase with respect to time of population P is directly jointly proportional to the population, okay, and the difference 5 maximum minus P. Jointly, first function, second function as one, so they act jointly. Okay. The given condition is this. By the year 1900, the population of the Earth was 1 billion. You would see that as a time t equal to 0. And by the year 1950, after 50 years with respect to 1900, the population of the Earth was 2 billion. By the year 2000, we are now past year 2000, it is now 2022. But the problem was only asking for the population last 2000. What will be the population? The designation here is a small letter p is population in billions, t as actually the time in years. We will solve this one using differential equation. That's the importance of differential equation. Okay, let's proceed with the solution. dp over dt, we will start from here, equal to directly proportional. If we try to bring out an equality over here, we will place an equal sign here, and there should be a constant k here, okay, times the product of p times the difference of the maximum volume minus the population at any given moment, that is p times the product, the difference of 5 minus p. Okay, we put an equal sign, but we must have to place a k over here. There should be a constant here. Separating the variables, okay, we will multiply. That's why our topic is variable separable, differential equation, world population. Okay, we will multiply this one by 1 over p times 5 minus p. This is times dt. Okay. So sorry for that one. It should be dt times p times 5 minus p. Okay. So dp over dt times this dt here cancels. Okay. Okay, let's do it like this. We'll just move this one here, back here, then this d here, we put it here. So what will come out for this separation? There's no multiplication. Okay, dp all over p times the difference of 5 minus p equal to k dt. Okay, we separate the variables already. Okay, right? Let's try to solve the value of t as a function of time now. We will create a differential equation. This is actually our differential equation now. Right? So to solve for the population at any given moment, we will integrate both sides. Okay? We will integrate this one. Okay? But for the meantime, we could not integrate it. Let's try to compute first for the value of a and b. The integration of the left-hand side is actually using partial fraction under linear factors. There are two linear factors underneath, okay? This is p and 5 minus p. Recall your integration under linear factors. So we will take the equivalent of this one. Sorry for this one. This is with the p. Right? 1 over p, this one, times this should be equal to a over p plus b over pi minus p. Partial fraction, linear factors. Simplifying this one, 1 now will be equal to 5a minus ap plus bp. Okay? Then to compute for the value of a and b, we are now integrating. No, we are not yet integrating. We are just computing for the value of a and b. Equating coefficient of like terms, if you recall your integration under partial fractions under linear factors, we will equate first p to the first power. Left hand side, it will be 0. There is no term with the p on the left hand side, so this is 0. Right hand side, we got a negative a, and this is b. Right? So 0 equal to negative a plus b, or a will just be simply equal to b. Let's equate p to the 0, meaning the pure constant term on the left and the pure constant term on the right. If you recall your integration for partial fraction. P to the 0, the pure constant on the left is 1. On the right hand side, we are now through with this. So this is equal to 5a. 1 is equal to 5a, therefore a equal to 1 over 5. And since a is equal to b, this is also equal to b. So we now know the value of a and b. Okay? Therefore, if we try to integrate dp over p times the difference of pi minus p, this should be equal to, we are following this, the integral of k dt. The left hand side, after the computation of the value of a and b, this should now be equal to the integral of a over p plus b over pi minus p. This is 1 pip over p plus 1 pip over pi minus p, closed quantity dp. We are following this. Equal to, this is now integrable. This is kt, okay, plus k1. For the first two terms, they are both under natural logarithm, but let's try to verify the value of u. The value of u on the first one is p, du will be equal to dp. It is exact. It is exact. Well, we bring out 1 pip, so this is multiplied by dp. Du is dp, so it is exact. For the second one, the value of u is the one underneath, right? This is 5 minus p. Du is equal to 5 minus dp. It is not exact. It should be a negative thing. Okay? Because we bring out 1 pip, and the exact differential should have a negative sign here, so we will place a negative 1 over it, negative thing outside. So the integral of the first one should be 1 pip, the natural logarithm of p, plus 1 pip. We will place a negative sign because du should be negative, right? The natural logarithm of pi minus p plus kt plus k1. And if we try to combine this one, logarithm of a quotient, it should be the logarithm of the numerator minus the logarithm of the denominator. This is negative. So we combine under one natural logarithm sign, but this should be under the denominator. So this is 1 p, the natural logarithm of p over 5 minus p equal to kt plus k1. Actually, this is now the general solution of the population with respect to time. We got still problems, right? Because we do not know the value of k and the value of k1. Because we have to solve for the population as a function of time. So if you specify your time, we could compute for the population, right? But it's a must that we will compute for k and k1. But we are given two initial conditions. By the year 1900, or at time equal to 0, the population of the Earth was 1 billion. This is 1 billion. So we place t equals 0, p equal to 1 back here. This should be 1 pip, the natural logarithm of 1. 5 minus 1 will be 4, equal to k times 0 plus k1, but this is 0. Okay? You can compute this one using your calculator. We got the natural logarithm sign over here. I just simplify the calculation. I computed for the value of k1. K1 is actually negative 0.27726. Using your calculator, we got the natural logarithm sign over here. Okay? So we'll go back then at time, so we now know the value of K1, right? Okay. So let's try to compute for the value of K without the subscript. At time t equal to 50 years, by the year 1950, the population of the Earth was 2 billions. That is according to the scientists, right? At least you could Google what is the population last 1950, if it's really 2 billions. So we will place t equal 50 and p equal to 2 billions back here. We could compute for k. So this is 1/5 the natural logarithm of what will come out? 2 all over 5 minus 2, which is 3, equal to k times 50 plus k1, but k1 is this one. Right? You can compute for this one using your calculator. Okay? You place this one on the left, then divide that by 50. What will come out for the value of k without the subscript is 0.003923334. So if we try to bring out now the particular solution of the population as a function of time in years, okay, this should be 1/5 the natural logarithm of p over 5 minus p equal to 0.003923334 times time minus 0.27726. So we are now given p as a function of time. So this is actually a particular solution. Okay? We derive this using from the condition of the problem. So by the year 2000, or after 100 years with respect to 1900, 1900 plus 100 is actually 2000, right? So if this is 0, with reference to 0, year 2000 is actually 100 years. So at time t equal to 100 years with respect to 1900, what is the population of the Earth? It's an easy matter now because we already have derived population as a function of time. So this is 1/5 natural logarithm of p, which is unknown, over 5 minus p close quantity equal to 0.003923334 times 100 minus 0.27726. If you try to take the difference of this, it's 0.57537. But this is with the natural logarithm side. So to compute for p, we must have to eliminate the natural logarithm side. We must have to take the antilog of both sides. And the antilog of the natural logarithm is simply written like this. E to the natural logarithm of the ratio 5 over 5 minus p equal to e raised to 0.57537. This is antilog, this is antilog. And e raised to the natural logarithm, okay, I will place it here, guys. Hold on. So you will not get lost. What comes out? It will become p over 5 minus p equal to e to this is actually a certain value. I think, hold on, I'll bring out my rough draft over here. This is 1.78. So it will be p equal to 1.78 times the difference 5 minus p, right? P equal to 1.78 times 5, okay? 1.78 times p will be negative 1.78, right? We will place it on the left, so this is plus 1.78 p is plus. This will now become plus after the transposition. 1.78p plus p is actually 2.78p equal to 1.78 times 5. And p now will be, you multiply this by 1 over 2.78. Left hand side, this cancels. P now equal to 1.78 over 2.78 times 5. And P is actually equal to 3.2 billions. 3.2 billions. So according to our computation, last year, by the year 2000, okay, we passed that one already because it is year 2022. It says the population of the earth was 3.2 billions. You could Google this one if this is correct. Because as of now, 2022, the population of the earth is 7.7 billions. Right, guys? Oh, that's the importance of integral calculus. I want to say something about this, but it's to, there might be some political consequences. I don't want to say it, right? The population of the earth now is 7.7 billions. We got the pandemic. So if we lose many billions, we could reduce this one because scientists says that the earth can only sustain 5 billions.